Welcome back to an introduction to real analysis. We continue working through section by section. We're now in chapter 2, section 4, Cauchy sequences. What are we going to discuss here? So the previous working definition of a limit of a sequence, absolutely crucial to understanding real analysis, but there's kind of a central problem. To prove a sequence converges, through that definition, you generally need to know in advance what you want to show it converges to. The monotone convergence theorem does give us a way to show a sequence converges without a priori knowing what the limit is, but monotone sequences are not the usual situation. So the notion of a Cauchy sequence provides another way to show a sequence converges, but you do not need to know in advance what the limit should be. So here is the definition. A sequence xn is called a Cauchy sequence if, for every positive epsilon, there is a cutoff index m, so that for any two indices past that point, the distance from xn to xk is less than epsilon. And here it is presented symbolically, which will inform how you prove a sequence is Cauchy. For any positive epsilon, there is a cutoff index, so that given any two indices that are beyond that point, the distance between those relative terms of the sequence is less than epsilon. So let's talk about this definition. Informally, being Cauchy means that the terms of a sequence are eventually very close to one another. We have a distance between x sub n and x sub k here. Now it only works for indices past a certain point, hence the term eventually, but the terms of the sequence are close to one another, their distance being the absolute value of the difference. So the distance is less than epsilon past a certain point. Now we might expect such a sequence to be convergent, and we would be correct due to the least upper bound property. We'll have to prove that, of course. But before we prove it, we're going to look at some examples. Here is an example. 1 over n is a Cauchy sequence. So let's prove it. Because the definition starts with for an arbitrary epsilon, let epsilon be arbitrary, we now have to find an m. So again, thanks to the Archimedean principle, there is an m which is bigger than 2 over epsilon. So for any two indices past that point, first of all, 1 over n and 1 over k are both less than epsilon over 2. Therefore, the distance between 1 over n and 1 over k, thanks to the triangle inequality, is no larger than the absolute value of 1 over n plus the absolute value of 1 over k. Absolute value is not necessary here, but both of these are less than epsilon over 2, and we're done. Here's another example. We'll show that the alternating sequence, -1, +1, -1, +1, and so forth, is not Cauchy. So let epsilon be positive, but also let it be less than 2. Now given any index, two consecutive terms, so pick an n, and then let k be 1 larger. So one of these is +1, and one of them is -1. So you either have -1 times 1 minus -1, or +1 times 1 minus -1. In any case, the absolute value there will work out to be 2, and 2 was larger than epsilon. So it doesn't matter what m is, I can find two indices past that point where the distance between those two terms of our sequence is larger than epsilon. So this definition failed. For any epsilon, nope, as long as epsilon is less than 2, then for every m, there exists a choice of n and k where this fails. So this sequence is not Cauchy. Let's take a look at proposition 2.4.4. If a sequence is Cauchy, then it must be bounded. This is a little preliminary result working towards our eventual proof that Cauchy sequences must converge. So as a proof, suppose that you have a Cauchy sequence. In the definition of Cauchy, set epsilon equal to 1. So past a certain point, any two terms whose index is sufficiently large, the distance between them will be less than 1. So by the reverse triangle inequality, if I simply let this one be m, right, this holds for any two choices of index larger than or equal to m, so pick one of them to be equal to m, the reverse triangle inequality will give us that the absolute value of xn minus the absolute value of xm is less than 1. In other words, the absolute value of xn is less than the absolute value of xm plus 1, and this holds for all indices past capital M. So our sequence now comes in two collections. Everything of index up to m, but not including. That's a finite set. All finite sets are bounded. All indices past m, the absolute value is bounded above, therefore the collection of values for index larger than m is also a bounded set. So the finite set up to index m, bounded. Everything after that point, bounded. So their union, the entire sequence, is also bounded. Okay, theorem 2.4.5. This is the real point here. A sequence of real numbers is Cauchy if and only if it has a limit. So let's prove it. First, suppose the sequence converges. We will have to show that it is Cauchy. Denote the limit as x and let epsilon be positive. Because the sequence converges to x, there is an index m, so that for all indices past m, the distance to the limit is less than half epsilon. So now pick two indices past that point. We want this to be less than epsilon, but I can just throw in a minus x plus x and throw the triangle inequality at it. But since both of these indices are bigger than m, for both of them I get less than epsilon over 2. So if the sequence converges, eventually every term is close to x. If every term is close to x, then they are all pretty close to one another. That's the gist of this argument. So from the fact that the sequence converged to x, we got that it is Cauchy. How about the other direction? Now let's assume we have a Cauchy sequence. We need to show that it converges. The trick here is we don't know exactly what it's converging to. However, we do know that a Cauchy sequence is bounded. Therefore, it has a lim_inf and a lim_sup. Denote by A the lim_sup and by B the lim_inf, and then let epsilon be an arbitrary positive number. So there must be a subsequence converging to the lim_sup and a different subsequence converging to the lim_inf. Our goal now is to show that the lim_sup and lim_inf are equal. We will then be able to claim that the limit must exist. Okay, so here's what we have so far. A Cauchy sequence with lim_sup A, lim_inf B, one subsequence converging to the lim_sup, a different subsequence converging to the lim_inf. Epsilon is an arbitrary positive amount, and we want to show that the lim_sup and lim_inf are equal. So there are three different cutoff indices, m1, m2, m3. The sequence x sub n sub I is converging to the lim_sup, so past a certain point, every term of that subsequence is within epsilon over 3 of the lim_sup. Past a different index, x sub m sub I is within epsilon over 3 of the lim_inf, and also because the original sequence was assumed to be Cauchy, for all indices past some other cutoff m3, the distance between terms of the sequence is less than epsilon over 3. Now let capital M be the largest of all three, and note, if I is at least as large as m, then n sub I is always at least as big as I, so n sub I is as big as m3. M sub I is at least as big as I, so m sub I is at least as big as m3. So we have three different things here. We are past a certain index for which all of these inequalities hold, meaning x sub n sub I is within epsilon over 3 of A, x sub m sub I is within epsilon over 3 of B, and x sub n sub I and x sub m sub I are within epsilon over 3 of each other. So just to summarize, we have past a certain index, x sub n sub I is within epsilon over 3 of the lim_sup, x sub m sub I is within epsilon over 3 of the lim_inf, but x sub n sub I and x sub m sub I are within epsilon over 3 of each other. We just want to show that the lim_sup equals the lim_inf. So let's look at the absolute value of their difference. The absolute value of A minus B, I do a minus plus xni and a minus plus xmi, and now I'm going to throw the triangle inequality and break this up into three terms, each of which less than epsilon over 3. Therefore, the distance between the lim_sup and the lim_inf is less than epsilon, but epsilon was arbitrary, so the lim_sup and lim_inf must be the same number. Therefore, the sequence converges. So let's briefly discuss this Cauchy criterion. We just showed that a sequence of real numbers is convergent if and only if it is Cauchy. This can be used to define what completeness is in the real numbers. So we can say that a set in general is called Cauchy complete, or maybe just complete, if every Cauchy sequence converges to something in that set. So the way we've approached this is we started with the reals as having the least upper bound property, and we have eventually worked up to this point to show that Cauchy sequences of real numbers converge to real numbers. In other words, the reals are Cauchy complete. Now, what one can do as a bit of a modification is complete the rationals by adding in just enough points to say that Cauchy sequences converge. So you can make a sequence of rationals that is a Cauchy sequence but does not converge to a rational number. What you would then do is you'd say, okay, start with the rationals and add in enough formally defined values so that any Cauchy sequence converges to something in our set. Maintain the fact that it is a field and ordered. Now you can recover the least upper bound property from this Cauchy completion. And then you will have constructed the real numbers. Now, one way that this is a bit advantageous as a construction to define the real numbers through the completion via Cauchy sequences of the rationals is that is something that can be generalized to more abstract settings like metric spaces. This will be seen in more detail much later in chapter 7. Now, the Cauchy criterion is stronger than just saying the difference between consecutive terms goes to 0. What's important in the definition of a Cauchy sequence is that these two indices are completely arbitrary past a certain point. They are not just adjacent indices, and they're not just within j of each other for some fixed j. So shortly, we'll start talking about series. When we get to partial sums of the harmonic series, for example 2.5.11, we will be able to construct a sequence so that the limit between consecutive terms goes to 0, but the sequence goes to infinity. Or more generally, the limit between two terms whose index differs by any fixed amount goes to 0, whereas the sequence goes to infinity. So compare that to exercise 2.5.12 for reference. The key point in the definition of Cauchy, again, n and k are completely independent of one another. They might be very, very far apart. N and k are any two indices past capital M. There's a lot of numbers that are larger than m. So let's review what we talked about. A Cauchy sequence of real numbers. Ultimately, we showed this definition is logically equivalent to a sequence converging. It was an if and only if after all. But the definition begins a little bit differently. Rather than needing to define a sequence having a specific limit L, which would require us to know what the limit is before we can attempt to prove that the limit is L, the definition of a Cauchy sequence only requires us to be able to compare terms of the sequence to other terms of the sequence without knowing in advance what the limit is supposed to be. So they are equivalent definitions in the end, but sometimes it's possible to show a sequence is Cauchy without needing to know in advance what that limit is supposed to be.